Okay, so we will start now. Good morning, everyone. I hope you can hear me. Okay, perfect. So thanks everyone for joining and welcome to this webinar hosted by Fatigue4Light and Revolution projects, which is called Electric Vehicles Lightweighting Assessment based on Artificial Intelligence, Machine Learning, and Numerical Modeling using new materials. Before we kick start, my name is Andrea Prieto, and I will be your host for today's webinar as member of the Revolution project from Aidener. I will have the support of my colleagues from EURECAT as member of Fatigue4Light project, who will be giving assistance out of camera. So we will start. During today's session, we will see presenting some experts from Sydney and the Polytechnic University of Catalonia on behalf of the project Fatigue4Light, and from Aidener and FARPlus on behalf of the Revolution project. Although further details about each project will be given in a minute, both of them has a common objective, working on lightweight materials for electric vehicles, promoting their eco-design and a more sustainable mobility industry. This webinar will be divided into three sections. The first one will give you the context of the two European projects that are hosting this webinar. The second session will go through the technical work behind both projects, why and how machine learning and numerical modeling are being applied. And the last session will be a roundtable with numerical modeling and machine learning experts, where current and future trends will be discussed. At the end of each section, we will give you the opportunity to ask any specific questions regarding the presentations. And for sure, in the final roundtable, we will have some time for your direct or by chat interventions also. Okay, so for the first session, we have today with us both projects coordinator. We have Sergio Jimenez from Fatigue4Light and Emre Elmas from Revolution. Thank you both for joining us. Now I will give the floor to Sergio Jimenez. Thank you.
Okay, thank you, Andrea. Just to confirm, can you hear me?
Yes.
Yes, Sergio.
Okay, perfect, thank you. So, as Andrea was telling you, I will start with this first part of today's webinar. First of all, thank you everybody to join us in this webinar. And the idea for this first part of the webinar is just to briefly introduce you the work that we are doing from these two projects, the Fatigue4Light and the Revolution projects. And as the coordinator of the Fatigue4Light project, I will be talking now about like 10 minutes for introducing you what we are doing for this Fatigue4Light project, which are the objectives and so. And basically, I've prepared this presentation following this structure here, in which I will first of all give an overview of the Fatigue4Light. Then I will introduce the consortium, introduce the objectives in the Fatigue4Light, talk really briefly about the research beyond the state of the art, introduce which are the concepts that better define the work that we're doing in the Fatigue4Light project, really briefly introduce which are the new materials that we're using to address the objectives in the project, and finally I will briefly discuss about the phases that we are following all along the project. Okay, so the Fatigue4Light project, the entire title is Fatigue Modeling and Fast Testing Methodologies for Electric Vehicles Chassis Weight Reduction. This is an H2020 project being granted under the topic of Advanced Light Materials and their Production Processes for Automotive Application. This is a 3-year project, and we are about to finish it. Well, we will finish it by the end of January. So we've just started at the very beginning of the year, the last year. in our project. A total of 13 partners coming from Spain, France, Italy, and Sweden are working in this project, and the project is being coordinated by THIMNE, which is the research center in which I'm working. Okay, so three research institutions are working in the project: THIMNE, Eurecata, and the Fiat Research Center. Three universities: the Lulia University from Sweden, the Polytechnical University of Catalonia (UPC) from Spain, and the Politecnico di Torino from Italy. Six industrial partners: Magneto Wheels, ArcelorMittal, Gestam, Rice, Profiglass, and Composite Services, and one standardization body, which is UNE from Spain. Here you have a summary of the basic objective of the Fatigue4Light project, which is the reduction in vehicles chassis weight. And this mission, or in order to address this objective, what we are doing in the Fatigue4Light project is to introduce the use of new materials into these chassis parts in order to achieve it. So, of course, in addition to introducing the use of these new materials, we are taking into account eco-design and circular economy aspects, and we are also introducing the use of new tests, or we are developing the new tests, and we are also developing computer simulation methodologies to help into tackle this objective. And this is completely aligned with the European objectives, in the sense that the Fatigue4Light wants to help to build a zero-emission future by promoting design based on advanced numerical simulation tools. Okay, so with this you have now a better idea of what we're doing here. Basically, using new methodologies, new tests, following an eco-design and circular economy perspective, to achieve this weight reduction in the electrical vehicle. And what are we doing beyond the state, which is the research beyond the state of the art? Okay, basically, the Fatigue4Light is putting a lot of effort on the fatigue characterization of the materials being proposed to be used at the chassis level, and rather than characterizing the fatigue behavior of these new materials on the virgin state of the materials, what we are really interested in is on also characterize this fatigue response of the materials at the point when these materials are introduced within the chassis. This is after the manufacturing processes. And this means that in the Fatigue4Light project, we are really interested in studying which are the damages or the nonlinearities introduced by these manufacturing processes in the new materials being considered, such as cutting, forming, and welding processes. And not only characterizing these direct effects in a monotonic sense, so studying the monotonic, which is the monotonic influence or the influence in the monotonic response of these materials, but also we are interested in characterizing which is the effect of this manufacturing process, the degradation introduced by these manufacturing processes at the long term. So we are interested in studying which is the fatigue behavior of the material, or the changes in the fatigue behavior of the material once the material has been submitted to manufacturing processes. And here there is like a summary of all the concepts that better define the work that we are doing in the Fatigue4Light project. Basically, the basic ones that I've already introduced you in the objective slide are this one here, related with the introduction of new and the use of new materials, such as high-strength steels or different types of metals, and the use of composite materials too. Also, the introduction or the use or the generation of new methodologies, new numerical methodologies, in order to assess this weight reduction at the electrical vehicle level, and everything with an eco design perspective. And of course, this simulation needs to be, um, let's say, directed, or we follow, or we uh, require, in order to better assess this numerical work. We need to complement this work together with monitoring. So we dedicate a lot of effort to monitor all the processes taking place the different at the different scenarios that we're considering for the Fatigue4Light project. And we also require the use of new advanced testing in order to be able to speed up all the work to be done, because the fatigue analysis from an experimental point of view is really has associated a really high cost in terms of time and money. And then here I've also written down which are all the materials that we are considering uh, to address or to achieve this objective in the Fatigue4Light project. So starting by introducing high strength steels in the for this purpose, considering complex phase steels, we are using CP800 and CP980. We are also considering the use of hybrid solutions made of GFRP or CFRP composites plus aluminum. And we are also considering or studying the use of stainless steels on this regard. We are also considering the use of press hardening steels, which are nowadays being used also in the automotive industry. And of course, as this is being used for the hybrid solutions, we are also characterizing several aluminiums to be used in the Fatigue4Light project. And I would like to finish this my first presentation with this slide here, which summarizes the work that we are doing, or that we are or the phases that we are following all along the Fatigue4Light project, in which we are adopting different type of perspectives along the project, depending on the phase in which we are work on the phase of the project itself. So we start at the very beginning by characterizing the material itself, the new materials that we are considering for finally addressing the objectives in the Fatigue4Light project. So there we adopt, first of all, a material perspective. Then once we've characterized these new materials, we move to this lab demonstrator perspective, in which we now are interested more in the processes, in the manufacturing process, and the effect that these processes have on the initial material that we've characterized at the very beginning of the project. And once we know the material properties and the effects that these manufacturing processes have on the materials, we finally move to this component perspective, in which we are studying directly real parts of the chassis of the vehicle to address there, which is the weight reduction that can be achieved by using the solutions defined all along the project. And through this whole process, we follow always, or we consider 3 research lines that are always that are always applied together. So we define, or we follow always an eco design perspective through this life cycle assessment and life cycle cost analysis. We follow or we use experimental data at all the 3 stages. And of course, we use, or we follow this numerical perspective, this numerical research line, to address also, or to characterize the numerical, or to define the numerical methodology that it's being built in this Fatigue4Light. And with that, we obtain what we call the Fatigue4Light solution. Okay, thank you very much for your attention, and maybe we can move to the revolution presentation, and then we can just proceed with the questions for this first part. Or I'm not sure, Andrea, how you want
Yes,
to
yes.
proceed. Okay.
Yes, thank you, Sergio. Yes, now Renas will be sharing the revolution context as the project coordinator. Thank you.
Thank you very much, Andrea, and also thank you very much, Sergio, for your presentation. And besides, thanks to all participants who joined us today to learn more about the Fatigue4Light and also Revolution projects and for your valuable times. Now you shall be able to see my screen.
Yes.
Yes, okay, that's great. I'm Emre Yılmaz, and I'm the coordinator of the Revolution project, and I'm working as a fundraising and project responsible for FAR+ and FAR Labs, which are located in Turkey. And FAR+ actually is a Tier 1 automotive company which designs and manufactures exterior and interior composite trim parts for the vehicles. And actually, I'm here on behalf of Revolution and to introduce to how Revolution project is contributing to the ecosystem and also to industry. Firstly, the title of the Revolution project is Supporting the Electrical Vehicle Revolution through maximizing electric vehicle range and end-of-life vehicle recovery through optimization of recycled plastics and advanced light materials. Actually, the title of the revolution expresses how the revolution, what the actually revolution targets, and also to achieve, and also how it will contribute to the ecosystem. But of course, we will go to the deeper of the revolution. And the revolution has been started also like the Fatigue4Light in the beginning of the 2021, and also the deadline of the project, expected deadline is at the end of this year. So, however, the total project budget is about 6 million euro. The European Commission contribution budget is about 5 million euro. And this project has been funded in a core topic, which was an innovation action. And what is the revolution? Actually, the revolution project is bringing a new open loop recycling technology for the automotive injection molding processes. And the aim of the revolution is to optimize the usage of recycled materials in the injection molding process by the support of machine learning and artificial intelligence technologies that will also be developed in the project. So by these technologies and the processes, of course, the target is to deliver high quality parts as well as the other virgin materials that have our other alternative existing alternative materials used in the automotive industry currently nowadays. So you know that using the recycled materials for the for the automotive industry, because of the high expected requirement, is so difficult, and also yeah, there are some strict rules that automotive OEMs are expecting from the manufacturers, and in that term, the optimizing the inputs of recycled materials and usage of these materials will be so critical for delivering high quality parts. And actually, as the Revolution Consortium, we are 14 partners which are coming from 10 countries, and actually, and in that sense, our goals, the main goals of the revolution, actually, while reducing the weight of components between 10% and 40% comparing to the current alternatives, also demonstrating at least 80% of the components as the recyclable and reusable. Actually, we can say that the Revolution project has few pillars like the developing AI and machine learning technologies, lightweighting, and also while using the recycled materials and also making the components as recyclable and reusable. For validating all these technologies, actually we have 4 use cases provided by several use case providers and also OEMs and the tire ones. So one of them is the backseat panel, the other one B-pillar cover, the next one crash box, and the last one is our rear bumper. Actually, before going to the deeper of the revolution project, actually I want to show you the actual automotive system, how the actual automotive system works. So as you know, the materials are coming from the mines or their sources, main raw sources as the virgin, and after that some processing, the materials are being used in the plants and factories. So after that, all these produced components are being sent to the automotive OEMs, and the automotive OEMs are combining all these components to make the full vehicle. And after that, after the when actually the vehicle has fulfilled its lifespan, or there is another thing, the components or the vehicles goes to the recycling process, and in there the components are being separated. Actually, in that sense, you can see now how the revolution is contributing all these industrial perspectives. So we are contributing in the plants, factories to make them more digitalized, and to make the processes, the injection molding processes, as smarter than the current alternatives. And after that, we are also focusing on the recycling process, as increasing the recyclability or the reusability of the components, and also using these recycled materials again in the factories to make the vehicles or the produced components. So you can see this industrial perspective for the electrical vehicles. And as I said, we are 14 partners are coming from 10 countries, and actually in those 14 partners actually are coming from the different level of the supply chain, different perspective of the supply chain. And while we have OEMs, automotive OEMs like the Tofaş, Fiat Turkey, and also Fiat itself, Fiat Italy, and its research center, CRF. We have also tire ones like the Mayer and Farplus. We have we have material developers, scale-up partners, and also like Aidenar, we have some technology developer, AI and machine learning partners. Besides also IMEC, it is a different perspective of the revolution, which are developing sensors. And Clariant, Lyondell Basel, Trinseo, Heatland for material development, and also the LCA, and also end-of-life vehicle works, and also search in the project, and Norner from the Norway for the scale up and also material development technologies too, as well as the VTT also. And when we look at the general overview, actually develop the machine learning and artificial intelligence will be used to optimize the recycled materials, and also by the support of rheometer technologies that we have developed in the project to monitor the flow of materials in the injection molding process, and also the data coming from injection molding machines and also process, as well as the sensors that we will implement in the injection molding. So all these data will be analyzed by the machine learning and artificial intelligence softwares for the optimizing input of recycled materials, and also their flows with the agents that used to increase the some specifications of the components and the materials. So actually the AI platform will also get data and use the data from 3 areas of the production process and to predict part quality also when using the recycled materials. And in here, the project, actually the Revolution project, will develop all these platforms that I mentioned, and then a range of recycled formulations, including self-reinforced materials and also some other PCR materials too. So in here, in the general perspective, lightweighting, superior performance, and end-of-life advantages also the scope that Revolution is targeting. And this is the implementation process of the Revolution. So optimize the advanced light materials, develop advanced process control, advanced process control, model and design the while process and also the materials and the components, and at the end demonstrate and validate all the results in the real life environment. So as I said, we have 4 use cases. The first one is the backseat panel, which has been provided by the CRF. And this component actually currently made of a formed steel sheet. And by the Revolution, actually, we will convert this component to an SRPO material with the lightweighting target of 55%, comparing to the current alternatives. And the second one is the B-pillar cover. Actually, this component is provided by the Mayer, and currently it has been produced as the 2K dual part, and we will convert this component in a monomaterial injection molded components by using the post-industrial recycled PMMA materials that we also developed in the project. So the next one is the crash box, which is provided by the Tofaş. Actually, it is the Fiat Turkey, and now this component is mainly produced by using steel, and we will demonstrate these components as a full polymer solution. Actually, this component is, since it is so long and big, we redesigned these components for the using of recycled materials aspect, and also for the lightweighting aspect. The last use case is the lower rear bumper, and it is a colored aesthetical part. And so there are some other expectations that we need to keep as the same with the current usage and with the current alternatives and the recycled materials used at once. So and these properties and specifications are both coming from the mechanical and physical side, and we will transform this component by PCR PP materials, and also our lightweighting target is 20% comparing to the current alternatives. Actually, these are all regarding to the Revolution project, and if you have any question, please feel free to ask, and also I will try to answer them. Thank you very much.
Thank you so much, Henry. Okay, let's see if someone has any specific question regarding this project presentation. If not, we will continue with the following section.
I think there is no question.
No, it seems so. Everything was clear. Okay, so thank you both for sharing this with us. We will jump to the next session, which is the technical presentation. Presenting the technical aspects, we have Lucía Galvez and David Pérez, both researcher engineers from IDENER, and Alejandro Cornejo and Sergio Jiménez, both as civil engineers from the Polytechnic University of Catalonia and Sydney. Again, feel free to use the chat for any possible questions so we can check them at the end of the technical presentations. You can proceed, guys. Thank you.
Okay. Can you hear me well?
Yep.
Yes, perfect.
Okay. So thank you very much, Andrea, for the introduction. We are going to start now with the technical presentation. Please go to the next slide. Okay. So the main focus of this first brief intervention is to state the both common points of both projects. As we have already seen, both Fatigue4Light and Revolution have the same objective, pretty much. And even if the approaches that they use are different, they both start by the data treatment. So starting talking about where the data is coming from in both projects, we have first of all the Fatigue4Light. They use different or make different experiments in lab, the monotonic tests, the fatigue data, and the residual strength test, from which they will give more details later on. And then in the case of Revolution, we perform some experiments using the injection molding machine that you can see in the right side of the slide. And this experiment gives some changing the parameters of the machine, gives some data that we can use later on for the development of the approaches. Then the data is treated in order to extract the real important information for the approaches. And then finally, the data is used for, in the case of Revolution, to build and validate the model, the machine learning model that we will be further integrated in the MPC controller. And in the case of Fatigue4Light, for the mechanical characterization of the materials to be used in the simulation. And right now, I'm going to give the floor to David, who will give more details about the technical approach of Revolution project. Thank you.
Thank you very much, Lucia, for this explanation of how both projects have things in common. Now I'm going to present the first approach, which is related strongly with machine learning, and it's from the Revolution project. So the presentation is divided in 4 points. And the first one will be just a very brief and this explanation about how neural networks actually work. I'm pretty sure that almost most of you already know this, but just as a quick recap. Then we'll move on to an AI pipeline, and this might actually be a new concept for more of you, so I think it's very interesting. Then we will move on and explain what is MPC, and it stands for Model Predictive Control. And this is the technique we used for the controller in the Revolution project. And then in the end, we will just take these 3 things and see how they are all implemented together in the project. Well, just before starting with this, I wanna say again in a little sentence what Emre said about the technical work we do in Revolution, which is just for an injection molding machine when we are using these AI and neural networks to optimize the input of the recycled materials for the injection molding process to deliver the best quality parts possible. Just so you have this in mind when reading all this. So then, this very brief introduction, if we need to define a neural network in 1 sentence, could be a digital copy of a brain, more or less, and it works. It is defined in different layers, which we can see here in the image. They would be the vertical pieces. And then each layer is divided itself in different neurons, which is represented by its circle. So this mimics the neurons in our brains, and they are interconnected with different weights and biases, and they are nothing more than just numbers that they multiply and add up, and then magic happens, let's say. Then there is an activation function at the end of each layer that determines which part of the information is passed from one to another. And the real important thing is that this architecture can be actually trained with data, and it can learn. And this is just a very simple example, but the possibilities are almost endless, as you can see, for example, with ChatGPT nowadays. It's actually mind-blowing. So now moving on with the pipeline. This is, it was even a new concept for me when I started the project. And it is, in summary, an automatic continuous system that integrates, develops, and updates a machine learning model. And this is done automatically, and it's based on the MLOps solution. In our case, we are using Apache Airflow as the orchestrator. And in this image, we can see the approximate structure. So it goes from ingesting the data from the server of the FARPlus servers. We then validate it, pre-process it, and it tries to train and searches for the best hyperparameters to train a model that actually adapts to the current data trends. And then this new model, this possible new model, is compared and evaluated with the one in production. And if the performance of the new one is better than the production one, it just gets updated. It's and pushed. And all of this is done automatically without any human intervention. All the data is stored, and it's actually very, very powerful and saves a lot of time. Here we have just another screenshot where each line represents a different stage, and we can see, well, that everything is green. In this test, everything worked perfectly, and the new model was developed correctly. Then, once we have the neural network developed, we need to move on to the actual control of the machine. And the chosen strategy is MPC, which is actually rather complex, but also simple in a way. It's an iterative strategy, and it's based on the model of the process, which for us it's the machine learning model, and it relies on minimizing an objective function at each step, while also satisfying some constraints that are inherent to the process. So in this next slide, everything will be made clear. As I said, it's a discrete strategy, so the time steps are clearly defined, and each cycle is composed of 3 main steps. Let's take a look at this image. So the horizontal axis is the time, and each k is a different step. And here we have the red dotted line, which will be the reference trajectory for the output. And this yellow and golden line is the actual output. So we want to get the yellow line to be in the same level of the red line, just a simple control reference trajectory. And here we have the blue and turquoise lines are the predicted and the inputs and the predicted inputs. So once we have an image of how the system works, at each time step, first, all the different parameters and variables of the process are given to the MPC, the inputs, outputs, if the constraints have changed, everything, the new data is updated. Then, and here is the actual power of the MPC and why it is very robust. It calculates for a prediction horizon that it's predefined for a number of steps. It calculates the input necessary such that the output reaches the reference at the end of this horizon. So in theory, if we applied all of these steps, the output would follow this line and meet with the reference. But instead of applying all of these steps, we just apply the first one. So this value will get updated and then everything is done again. We receive the new data, we move on with a larger prediction horizon and so on. So this is why it's very robust, because you can have disturbances, strong ones, change in reference trajectory, any change in constraints, and this iteration process will make sure that everything is controlled perfectly. Okay, and now the important and fun stuff, how all of this comes together for the Revolution project objectives. So the main approach is divided into two steps. The first one is the AI pipeline that generates the AI model. And the second one, the MPC and the controller. So in this small diagram, we can see that new input data arrives. It would be passed on to the pipeline, develop the new model. If it is better than the previous one, it will get updated. And if not, just that data will be stored for whatever later purposes. And then here, the MPC is divided of this model and the optimizer. And so with help of the optimizer, which I will explain on the next slide, it generates all of these predicted values of the inputs such that the outputs are, well, as close as possible to the reference. And now lastly, how does this optimization happen? This is implemented directly with the TensorFlow library, and it works in actually a pretty innovative and powerful way, because the model, which is actually the AI model, is divided into two parts. Here on the right, we have the trained layers, which is this previous model, just the model that takes all the input data of the machine and predicts the optimized data such that the quality is the best possible. So once we have this pre-trained model, we freeze all these layers. And what does freezing the layers mean? That they are no longer trainable and the values are static. So nothing happens here. And now the magic happens on this first layer. We insert a new layer at the beginning with a neuron per its input parameter. It's all initialized at 1, so just multiplying by 1 does nothing. But then we train this new model, which has an extra layer at the beginning, and TensorFlow does with gradient-based optimization, optimizes this layer, which is just training another neural network model, such that the output is, well, the quality is the best as possible. So now we have here the predicted quality, and directly the values of each of the neurons are the optimized value of the inputs. And we can just repeat this process at each iteration, and we get the output and the input optimized. And this has been the brief explanation. Thanks you everyone for your attention. If you have any questions, we'll just wait for my colleagues from Fatigue4Light for the technical explanation, and then feel free to ask them. I will now leave them for their presentation.
Okay, thank you, David and Lucia. Let me just share my screen again. And just to confirm, you can hear me properly, right?
Yes.
Okay. So now we will more or less proceed in the same way as Lucia and David have done for the Revolution project, but now for the Fatigue4Light. So in this presentation, we will be focusing on the numerical methodology that we are using to for the Fatigue4Light project. This will go more or less in the direction of my initial presentation. So basically, I will go more in depth into the numerical methodology topic. Okay. We've structured this presentation now with these three main topics. First of all, I will briefly develop a little bit more the slide that Lucia has presented about the experimental information that we're using and how we use that, or how we take that into account, or the purpose of using this information from the numerical point of view in the Fatigue4Light project. And then Alejandro will introduce you, or will explain which are the main the basics of the numerical models in terms of fatigue modelization, and also sorry, for fatigue modeling, and also for modeling the behavior of composites that we are following in the Fatigue4Light project. So let's start with this from experimental data to computer analysis. As Lucia mentioned previously, basically in the Fatigue4Light project, we use experimental data coming from some basic tests, such as the monotonic test. So we use here force displacement information and fatigue data in terms of high cycle fatigue information. So stress, we use the typical number of cycles towards stress information, so SN curves basically, that characterize the high cycle fatigue behavior of the materials that we are using in the project, together with some more advanced tests, such this residual strength test, which is a combination, in fact, of a monotonic and a fatigue test itself, themselves, meaning that we applied a certain number of cycles, and then to this material that has been submitted to fatigue, then we applied a monotonic test, a tensile test, and we study there which is the degradation induced by this amount of cycles into the monotonic response of the material. And we use this information to fit our numerical model, as Lucia mentioned. But in addition to this, so I mean, where we use this information, this experimental information, as I was mentioning you, we use this information to build our model. So basically, the objective of this part of this use of the experiment is to characterize the material that we are studying in the project. So the high strength metals, the composites, the aluminum, the press hardened steel, and so for all of this material, we've done the same type of experiment analysis, and we use that information to characterize the material from the numerical point of view. So all this information, all these experiments are based, or all this experimental information is obtained directly from standard specimens, and we adapt this information, this experimental information, so force displacement and number of cycles and stress info, into the information that we require to fit our numerical model. Then we also use experimental data also to validate the model that we are proposing in the Fatigue4Light project, meaning that rather than now focusing on building the numerical model itself, once we've built it, we move to this validation process, and meaning that now the objective that we are pursuing is the process itself. We are interested in understanding which is the non-linearities introduced by the manufacturing processes taking place while building the components that are used at the chassis level of the electric vehicles. So at this step, we are also using experimental information to validate our numerical model, because then these experiments that are done now at lab scale demonstrators, we compare the results that are obtained experimentally with the ones that we obtain numerically. And this allows us to prove the versatility of the numerical model that we are building, because then we are proving that the methodology that we define through the Fatigue4Light, it's not only valid to characterize the basic monotonic and fatigue behavior of the material, but also we can use that to predict which is the behavior of those materials when they are really applied into the automotive industry. And then we also use experimental information to explore the potential of our numerical methodology. And in this case, the objective here is pure research. But also something that then can be used and applied by the industry. In this scenario, now once we know that we have characterized the material, and once we've validated the model and we know that we are able to capture the behavior of the material once it has been subjected, when the manufacturing processes have been applied to that material, we can then move to these demonstrators, which are the ones that are being studied in the Fatigue4Light project. Here you can see this is a low control arm used in the suspension in a vehicle. But of course, we are also studying other type of demonstrators like wheels and shock towers, and also beam elements in the chassis. And then there what we pretend from this analysis is to make sure that we end up with defining a methodology that can be used to assess the industry along the design stage. So this is the basic aim of or all the applications of the experimental data or the experiments that we perform all along the Fatigue4Light. And finally, I would like to briefly introduce the uses of the numerical methodology that we are building all along the Fatigue4Light through these three highlights, let's say, because this numerical method that we've developed for the Fatigue4Light allows us to reduce cost and time, assess complex cases, and understand the governing phenomenon, which is taking place during the degradation of the materials or the demonstrators that are being studied. So let me just start with this reduced cost and time. And this is really dedicated to the fact that we are studying fatigue processes, and fatigue in terms of experimental point of view, it's always related with a lot of time and a lot of samples to be used in order to characterize the behavior, the fatigue behavior of the material being studied. So in this way, combining experiments and the numerical methodology, we end up by reducing this initial state, the current state in which one SN curve of a material is usually characterized, or the characterization of one SN curve takes 1 month when doing a complete experimental campaign. And with both the experiments that are the new experiments that are proposed in the Fatigue4Light project, and also combining this with the numerical technology that we are proposing from the Fatigue4Light project, we are reducing a lot of this time here, and also the cost associated to this fatigue characterization. The assessment of complex cases is related with the fact that usually the type of software that is used in the industry, or that is used nowadays to characterize the fatigue behavior, is only dedicated to the simple cases in which you are just interested in obtaining a number, saying that or defining which is the amount of cycles that a specific geometry will withstand based on previous experimental data and an elastic characterization of the or elastic study of the geometry being studied. By using the numerical approach that we are proposing, we are moving from this strategy that is really commonly used towards a strategy in which we are combining this fatigue study of the fatigue degradation coming from the application of cycles in a geometry with an isotropic damage model that allows us to identify both the crack initiation and also the propagation of that crack along the life of the material. So we are able to take into account changes in the loads being applied, for example, along the life of the material, which may generate different evolution or complex evolution of the crack that causes the final failure of the geometry being studied. And this here, understanding the governing phenomenon, this is of course also related with the fact that the available technology used while characterizing the fatigue failure is usually these technologies usually supported or uses all those numerical studies are based on elastic predictions, and this doesn't allow to correctly understand which are the non-linearities that are taking place during the fatigue failure of the components being studied. And so this makes really necessary to improve or to use different technologies to better address this type of research. And so we propose the numerical methodology that Alejandro will describe to you right now. So Alejandro, whenever you want.
Thank you, Sergio. Well, let's dive in a little bit into the math behind this fatigue modeling. Actually, before the Fatigue4Light, and especially during the Fatigue4Light project, we have been working a lot in developing this kind of material laws, let's call it like that, or constitutive laws within our field, which is a way of relating a strain state with stresses. Okay, and this can be done in many ways. But in terms of fatigue, and in here we're going to focus in high cycle fatigue. Okay, so 10 to the 5 plus cycles. And mainly, in order to use our numerical model to predict fatigue failure, we are based on we could be based on any discretization technique. We have chosen to be the finite element method, but it could be any other discretization. And basically, we need pretty standard material parameters like Young modulus for the stiffness or Poisson, the yield limit of the material. This is for non-fatigue related, but if we really want to manage or to be able to simulate fatigue, we need a set of fatigue parameters. Well, in this case, our model is also based on standard information, in this case, based on the Wöhler curves, okay, that can be obtained experimentally. And this Wöhler curves, which is the black line in the figure that we can see in this slide, relates basically a level of stress during the cyclic loading with a maximum number of cycles that material would be able to withstand without start cracking or developing degradation. Okay. In this case, to model this effect, we introduced in our model the so-called fatigue reduction factor, this F-ret, which is represented by the red dashed line. And in the next slide, we will see how it is computed and accounted in the model. Well, I'm not going to get into the many details, but well, based on this Wheeler curve, we can compute a fatigue reduction factor, this F-ret, which will depend on several material parameters that can be estimated with experiments, and obviously based on the number of cycles, n sub c in this case. Well, our model, our constitutive model, is based on a damage constitutive law, which means that the nonlinearity or the degradation of the material is accounted by a loss of stiffness, not by developing plastic strains, but with a loss of stiffness, which is the behavior that it is expected according to the experiments. And this damage degradation is defined as a D in the stress definition of the model. Well, but this damage, the standard damage constitutive law, doesn't have any way to include the effect of cycle addition. So in the yield criterion, which is the second equation that we can see in the slide, which is a way to verify if we are inelastic or in non-linear behavior, and it can be according to many yield surfaces, which we can see the expression is a certain measure of stress minus a certain measure of the strength of the material. So if the strength is greater than the stress, this is lower than 0, so we are in elastic regime, everything is linear. But if not, we have to account for any mean of degradation, in this case damage. Okay, so fatigue is introduced in this model by dividing the stresses, the normal stresses that the sample is exhibiting, by this reduction factor that initially is 1, but along cycles are increasing, the SF-ret will be reduced. So it means that the stresses will be amplified in order to accumulate this degradation due to fatigue. And well, this has some implications in terms of fracture energy and energy dissipation due to damage, but well, this is for reading the papers. Thank you, Sergio. Next slide, please. Okay, so how do we use this model? Well, as I said before and during the Fatigue4Light presentations, during the project, we have done an experimental campaign to be able to characterize in monotonic and in fatigue terms the different materials that we are using, like aluminium, steels, and so on. So we need the monotonic calibration for the stiffness and strength, and fatigue calibration for estimating the different material properties related to fatigue. And with that, we can apply the numerical model to any geometry, thanks to the special discretization of the FEM, like we can see in the lower left figure of the lower control arm. And well, we have performed several different kind of tests in relating fatigue, as Sergio mentioned before, like the residual strength experiments, in which we apply a certain amount of cycles and then we load it monotonically to see what is the effect of this degradation. And actually, this result is in the lower right part of the slide, number 3. That zone, the colorful zone, would be the zone affected by cyclic loading as a decrease of this reduction factor parameter. Thank you, Sergio. Okay, up to now, I've been speaking about the high cycle fatigue modeling to, let's say, a standard steel material or unique material, so no multi-component. So how do we apply this fatigue constitutive law or any constitutive law to composite materials? Well, we're going to see it in the next slide. There are many ways of doing it, like multi-scale or homogenization or other different methodologies. But in our case, historically, in our research group, we have been using homogenization techniques. In this case, for example, the serial parallel rule of mixtures, initially developed in 2008. And basically, this, let's say, constitutive law for composite modeling is mainly used to materials like the one depicted in this schematic figure. So we can see several layers. It can be formed by several layers, and some of them with oriented fibers embedded in some kind of resin or matrix material. And we'll try to fulfill mathematically several equations at once that they can be seen in the parallel and serial directions at the top of the figure. What does it mean? Well, in the direction of the fibers, we want to fulfill a parallel behavior, which means that strains are the same. But in the other directions, orthogonal to the fiber directions, we want to simulate or model a serial behavior in which the stresses are the same. And in order to solve this, we cannot do it explicitly, so we do it in an implicit way via a Newton-Raphson update of all the variables until we converge. And this works pretty well, and we have applied this to many, many different composite materials. For example, reinforced or pre-stressed concrete in nuclear plants, and also in glass fiber reinforced polymer, etc., etc. And for example, I mean, by applying this homogenization serial parallel rule of mixtures within the Fatigue4Light project, that we have several composite, highly complex, pretty complex composite materials. For example, on the left-hand side chart, which we have a composite material formed by, I think, 8 layers, because this is the denomination of the symmetric part. So we have one layer, 0 degrees rotation of the fibers, then another layer of 90, 0, 90, and then it's symmetrical. And we can simulate that even depending on the case, but since those cases were tensile, even with one finite element at constitutive level, we can homogenize the behavior of those layers. So it's a highly efficient methodology, but also not only 0 and 19 can be modeled. So in the right-hand side chart, we can see that we are also getting really good results in combining 0, 90, 45, minus 45 rotation. This rotation can be arbitrary and selected from the input data. So, and the good thing is that we don't have to recalibrate anything. Once we characterize the matrix and the resin, the serial parallel rule of mixture is able to compose the behavior of each material with the corresponding rotation, volumetric participation, etc. So there is only one calibration, and then all the layers and combinations are automatically accounted. And now lately, especially with our very good PhD candidates, we have been working in generalizing the fatigue modeling or failure in composite materials. So we're going to try to combine this serial parallel rule of mixtures, which up to now has been mainly used in monotonic loading, combine this serial parallel with the fatigue constitutive law that we have seen at the beginning in order to simulate failure in highly complex composite materials. Well, up to now, experimentally, we have at the right-hand side chart a few information. No? For example, the lower part, the glass fiber reinforced polymer fatigue data that we can see comes from experiments, okay? But the reality is that we cannot use this information because the serial parallel rule of mixtures works with component-based information, and this fatigue data is for the whole composite. Okay, this distribution of layers of this composite, according to that stress level, withstands a certain number of cycles, but we cannot use that. So what we are doing now is transforming this composite information that comes from the experiments to equivalent fatigue of the fiber, which experimentally is the one that is experiencing fatigue. And then we calibrate to fatigue the fiber in order to, thanks to the serial parallel, obtain the proper fatigue life of the whole composite material. But this is work in progress. Then we can, okay. And one of the latest works that we have been involved in the Fatigue4Light, as Sergio mentioned before, we are working not only in standard composite materials, no, like the glass fiber reinforced and so on, but with hybrid solutions, which combine several layers of aluminium with glass fiber composite materials. And in order to simulate that, which is something that we are working on, we are planning to combine also this fatigue constitutive law with composite material manager. So we will be able to, by independently characterizing each of the components, for example, characterizing aluminium, the fibers and the matrix, both to monotonic and fatigue, the homogenization technique will be able to combine all this information and to hopefully estimate a good approximation of the fatigue life of this kind of complex and novel materials to be applied in automotive. Next, please, Sergio. Okay, so let's move to the brief conclusions. Regarding the numerical modeling, well, a good point is that this constitutive law, even that we have been using it for within finite elements, it can be used in any kind of discretization technique. Okay, so it's pretty general, and thanks to that, it can be applied to any kind of geometry, with the only limitation of the discretization technique, but not regarding the constitutive behavior. Thanks to the combination of this fatigue with homogenization techniques, we can assess this nonlinear behavior also with highly complex composite materials, with n layers and with all its generality in terms of rotations of the fibers. Another cutting-edge characteristic of the methodology that we have been working is that, okay, we are not only providing you the starting point of the fatigue degradation and the number of cycles in which it happens, but we can also see how it is the evolution of the crack, because it can happen that the crack can start in one particular point, but the problematic zone or the crack development up to failure can be different. Okay, so we can capture this kind of behaviors. And just for you to know, I mean, we have been developing all these methodologies mentioned in this presentation in technical terms inside an HPC platform, multiphysics. So it could be, and it will be from our side, potentially combined with thermal effects or any other kind of multiphysics problem inside Kratos multiphysics finite element code, which is open source and any of you can use now. So, and if you have any questions regarding that, you can contact us privately without any problem. And I think we are done with that part, so maybe we can move to the questions. Thank you.
Yeah, thank you.
Thank you both. So, yes, I saw there are some questions in the chat.
Yes, there are a few questions for me, I think, only for now. So
Yes.
I will actually share again some slides to try to answer them.
Perfect.
Okay, so for Fernando and Gerard, which are the two the people that made the questions, I think this new slide actually expresses very clearly how the system works. So we have this is the injection molding machine, the diagram of it, and for our approach, the input variables that are passed to the MPC, to the controller, are, I will just state the most important ones, but are the different pressures that are inside the chamber, the different temperatures also along it, the times required for the process, and then some material volume and some other minor parameters. And the output of the model will be just one, and it is the part quality. So it can be discretized in okay or not okay. So if the quality is enough for the piece to be acceptable, or if it is defined as defective and it won't work. So
the way I will repeat how it works. So at each iteration, we will get all of these input variables updated, and then the machine learning model will predict if with these parameters and the type of plastic that we have, what will be the output quality of the piece. So if the predicted quality is okay, the piece will be produced. But if it is not okay, so if it is predicted that the part will be defective, the controller will try to maximize that quality in order for it to be classified as okay. And well, here just paragraph of how we selected these variables and how they are treated in the next stages. And then I think Gerard asked something about regarding how if the optimizer is integrated directly with the machine learning model, and the answer is yes. So the weird and innovative thing about our optimization approach, which was this part, is that it is done directly with TensorFlow. And here I understand the question, but the answer is pretty simple, because a machine learning model is nothing more. What you do when you train a model is actually optimizing all the different values for the nearest and the weights and biases, such that the output is the required one. So in our case, we take advantage of these inherent optimization capabilities of training a neural network, and we implement this dual approach where we freeze all the previous layers and then add the new optimization layer. So when the model is trained and is optimized for the output, the only thing that can change is this new layer. So when it has finished optimizing, the values here are directly the values of the inputs, such that the predicted quality is the best possible.
Yeah, sorry, I'm the one who asked the question.
Yeah.
And sorry to interrupt. So once you have this, well, you can do this because you have the output, no? The output is 1, which is the piece it's in okay status or something like that, no?
Yeah.
So that now I understand why. Yeah, because in our problems this is quite different, and the output is not quite easy to to fix.
Yeah,
So
it's actually a bit abstract and a bit difficult, but we managed this approach, and
okay.
I hope now it's clear. Yeah.
And when you said something about maximize the quality, this is kind of weird, no? If you only have zeros and ones. So yeah, I know
So we have the 0 and 1. So it's hard to measure quality, but we're actually still working on it, on ways to define it better. But it's just a complex mixture of all these parameters and some other measured properties at the end, and then we just ramp it to this simple value.
Yeah. So then transform the ML problem to a regression model maybe, and then you will have like some variables that will describe this this quality somehow, and then define some soft restrictions also in the MPC.
Exactly. So such that, I don't know, temperatures cannot be negative, or like some simple constraints, and then everything works together, and the values get optimized.
Okay. Thank you, David.
Thank you for your questions.
I think there is another question in the chat.
How is the training data? Yeah, so exactly. The training data is the samples are defined with Actually, let me go back here. So this training, the actual data that we get in the raw format has more variables than the ones actually used for the training. And we then pre-treat and analyze them, and we select the best performing ones for the system so that we simplify a little bit. And then we use like 10, 15 variables in the end. Sorry. And when it also has the okay or not okay value. So if the part was with those data, if it was successful or defective, and we then take this to the model and train it. I don't know if it answers your question, Joaquin. Okay, so is there anything more? If not, we can move on with the next presentations.
Yep. We can move now to the last presentation.
Yeah. One second. Okay, I guess there are no further questions in the chat. Okay. So for the last section, for the round table, Sergio Jiménez and Alejandro Cornejo will be the moderators of the panel discussion, where Gerard Moore and Fernando Salazar will participate as machine learning experts from CINE, and Carlos de la Cruz and Álvaro Cabeza will do it as numerical modeling experts from IDNR. Just a reminder, the last 10-15 minutes of the session will be dedicated to your questions, so you could write them in the chat or open your mic to intervene after giving you the turn. Thank you.
Okay, thank you, Andrea. Let me share again my screen. So now let's move to this final section of today's webinar. And as Andrea has mentioned, the idea for this last part is just to initiate this roundtable by addressing some questions that we've prepared from Revolution and from Fatigue4Light side, to get a little bit more in depth with and so get a more general perspective of the topics that we've been introducing along today's webinar, from with respect to the numerical methodology and the machine learning techniques. So the idea here is to address these future trends and to, as I was telling you, initiate this discussion that can be then extended towards the audience. And in order to do that, and just to not repeat all what we've been saying, so rather than being Lucia, David, Alejandro, myself answering these questions, we've invited these four experts: Fernando Salazar, Gerard Moore, Carlos de la Cruz, and Álvaro Cabeza. We invite them to join this last part of the webinar, and so know which is their perspective on the questions that we will be introducing in the next slide. And the idea now then is to introduce these questions, to initiate the discussion, and so the experts will be giving their point of view with respect to those questions. And then, if necessary, Lucia, David, Alejandro, or myself can then connect also the question with the work being done in the Fatigue4Light and in the Revolution project. But before starting with the questions, I would like that Fernando, Gerard, Carlos, and Alvaro present really briefly themselves, just to know who is speaking then. So, for example, Fernando, if you want to start.
Okay, thank you, Sergio. My name is Fernando Salazar, and I am a civil engineer. And I've done most of my research on the combined application of machine learning and numerical models in different fields, in particular in dam engineering, but also in other topics.
Okay, then Carlos, for example.
Yeah, thanks, Sergio, for the introduction. My name is Carlos. I'm working at the DNR. I'm a computational chemist, and I've been involved in many mathematical problems or numerical methods applied to design new materials. That's why I'm here trying to answer your questions.
Okay, thank you. Then Gerard.
Hi, I'm Gerard Moore from CIMNE. I'm working in the Building, Energy and Environment Group, basically as a data science and project manager. I deal with daily with AI pipelines that we are dealing with in production for several buildings and building owners here in Catalonia, and basically modeling this the energy consumption of these buildings with black box models, machine learning. Yeah.
Okay, thank you. And finally, Alvaro.
So my name is Alvaro. I'm working at IDENER. I'm a chemical engineer. My background mainly focus on process engineering, process modeling based on phenomenological models, so numerical models, and also process assessments instead of techno-economics and life cycle assessment.
Okay, thank you. So let's start then with the questions. We prepared first 3 questions for dedicated specifically for each of the technologies presented. So first of all, we will be addressing some questions for the machine learning. So then Fernando and Gerard will be the experts that will be giving their answer to these questions. And then we will move towards questions for the finite element methods, or let's say numerical models. And then we've also prepared 3 more questions, which are more horizontal questions, and then all we will want to know the opinion of the 4 experts. So let's start with this first question for the machine learning topic, which is dedicated to talk about the data preparation and the data cleaning processes. So the question is, how important are data preparation and data cleaning processes, and fundamentally, on which parts of a pipeline do they have the most impact? And for example, Gerard.
Yeah, for me, these 2 steps, the data preparation, data cleaning, are key phases in machine learning pipelines. Maybe the most important, because we need to put the focus on obtaining the best data set as possible in this kind of techniques that we are using. And regarding these kind of pipelines, I think that we have multiple steps regarding data preparation. So for me, data harmonization, it's important. So translate each data source that we have to a common understanding of data. So to some ontology, it's pretty important, because it allows to make these pipelines reusable and easy to use for others. No? So once they harmonize the data in the same way, the pipeline it's reusable, which is a nice thing for open software and this kind of things. And a second step is to define data requirements properly so the validation of the data requirements. It's important to have this in mind in order to continue or not some pipeline, and this is important to define it in this this part of the pipeline. And also well, and finally, this last point, the outliers detection. It's also important for me, because I think that either they are large or small periods. So large could be periods affected with disruptive events like COVID, for instance, or a small period like error in sensors, communication systems, user behavior issues, something like that. It's important to detect them in order to or extract it from the data set that will be used for training models, or update their values regarding some models or some other technique. And it affects massively to these aspects massively to the data modeling process, which is maybe the main part, but it's not, for me, it's not the more time consuming, no?
Okay, thank you. What about you, Fernando? Can you give us your point of view about this?
Yeah, well, I mostly agree with what Gerard said. Of course, it's essential to have a good data set in terms of the amount of data, in terms of the quality of the data. And quite often, to spend more time in this preliminary tasks, let's say, in preparing, cleaning, reviewing, selecting variables, etc., than in the funniest part, no, when you have to want to train your models and actually applying them. But this part is essential. I mean, we often say that well, these machine learning algorithms are intelligent, but the thing is that they are based solely on the data that we provide them. So if the data is wrong, the output of your model is not going to be useful. So this part is absolutely essential. But this also depends a lot on the kind of problem that you are dealing with. And that's why I asked this question in the chat before, because there is a huge difference between the different fields. For example, in this particular case, in the Revolution project, well, the data comes from I don't know if experiments or actual processes in which parts are actually manufactured. Now, in other fields, for example, in the field where there are works, they work with sensors from maybe a large number of sensors, no? So they have a lot of data, and it's very easy for them to have more data. In other kinds of problems, for example, in the one in which we work more, we work in dams. So in dams, we typically have one record per week, or maybe per day if we are very lucky. And we have a lot of missing periods with no data. We have wrong data, and we cannot generate more data. Data is what we have. We cannot have data on situations that we would like to have a better model. So it depends a lot on the problem you're facing, but anyway, it's always very important. And my last remark on this is that it's very important to have the knowledge on the process, on the phenomenon that we are dealing with. I mean, this is not a matter, of course, it's a matter of dealing with data, but it's very important having someone who knows very well what is the nature of the problem, what is the nature of the variables, how this process works, and so on, so that we make the right decisions regarding which data to take, on how to decide if some value is wrong or not, and what's the reason behind this strange values and so on. So very important to have this, let's say, technological knowledge, not only an expert in machine learning or in data analysis, but also people who really know what's going on with this particular problem.
Yeah, totally agree. I'm not sure if you, David or Lucia, want to add something to this.
I think it was very clear. Just state again that data preparation and cleaning is also very important for the Revolution project, and we have a specific stage in the AI pipeline for these steps.
Mm-hmm. Okay, thank you. So then we can move to the second question, which is now dedicated to the retraining of the machine learning models. So the question is periodic retraining of machine learning models necessary? And can we define criteria to automate the process? I'm not sure if you want to go first now, Fernando.
Yeah, okay. Well, it is necessary. Is it necessary? Well, again, I would say it depends on the kind of model that you have, the how many records you have, and the cost of having more data and so on. If you have a model that is useful, then maybe it's not necessary to retrain it, at least not very often. It's always a good practice to try to improve it once you have more data. If we go back to the example before, in our case with dams, since we have very low reading frequency, it's well, of course we don't need to. It's not there's not a point in retraining your model with every week, because the change is going to be very small. So we typically retrain our models once a year, when we have relevant additional information for our models to be better. But in these cases, I see, and that's a question I would like to ask to David, because I saw that inside the pipeline you have this improvement of the model and evaluate the new model versus the previous one, and you decide whether to replace the one in production by the other one. So I would like to ask, how do you evaluate, and how often do you have a better model? I guess that quite often, because otherwise that step would not be inside the loop. But so it depends on the problem, and I would like to know David, your experience on this particular project.
Okay, yeah, we actually, the main purpose of the pipeline that we are developing is actually to do all this retraining of the model automatically. Regarding the frequency, we don't have that parameter specified yet, but it will not be that often. Like, for example, daily will be too often for this kind of process. I don't know, I cannot say you an exact frequency, but once we start the control implemented in the actual machine, we will see what are the data trends and how it develops, and then define the frequency. The nice thing is that this is just a number, and we can change it whatever we want, and then everything will be done automatically.
Okay,
So,
thank
yeah,
you.
It depends on the problem, and how often and how much data you can gather every day or every week.
Exactly.
Okay, and I would like to know then what's the general point of view, because as you said previously, they can obtain as many data as they want. So
Well, it's not it's not exactly like this, but we can obtain data. But if this data it's trash, then it's it's a problem. But normally we have a lot of problems with outliers and these kind of things, because we get data from meters. So that's why we have this type of data. But regarding this, the periodical retraining of models, I understand totally that it depends totally on the service that you need to provide. But normally in our case, we need to maintain or increase the level of prediction accuracy. We need to retrain it seasonally, like monthly, something like that. Depending on the type of building or the type of usage, because for instance, if it's a dwelling, maybe then it's weekly, but if it's a commercial building, then monthly it's more than enough, no? But in more complex machine learning pipelines, this retraining process is at the late times is linked to the evolution of some error metric, which is also quite nice, because when you try to retrain models for I don't know, 10,000 buildings, then the computational cost of it is not even you can have the data, but the computational cost is it's expensive, no? So you need to somehow automatize the process in order to update those models for those buildings that are not providing good prediction. So this is like the last situation that we are dealing with here in our group. So we are not making it seasonally; we are making it automatically depending on the error metrics that we are having from the buildings. Yeah.
Okay, okay, really interesting. I guess that we can move now to the last question for the dedicated specifically to the machine learning topic, which is now related with uncertainty. And it says, in case of using input data that come from the prediction of other models, how should we deal with uncertainty of this data in the model governing an MPC? Maybe we can start again with Gerard then.
Yeah, sorry for the noise. But in MPC, I think that it's important to assess the uncertainty of inputs, because, well, from my experience, we have mainly two types of errors, or two types of uncertainties in this case, which is the horizon biases, so the errors in predictions at multiple horizons, and then there's also the probabilistic uncertainties. No? So for the first one, imagine that that we are using the predicted outdoor temperature by a model which is used by an MPC, and normally this data will come from predictions provided by a weather API, for instance. One moment, I'm having problems. One moment. Yeah, someone was connecting me to another telco system. So for the first case, normally we get data from predictions from weather predictions provided by a weather API, and somehow these predictions are biased from the real local values of some building. No? So in this case, we should use at each time step of the training data of this model, we could use the temperature predictions at multiple horizons. So then the model itself can infer automatically the bias that it's and can consider it in the prediction itself without doing anything. You only need to provide the historical predictions of the data, no? And for the second type, which is the probabilistic uncertainties, sometimes when we use an input, this input it's an unknown value, no? It's not a single value. So we normally use aggregated values like the mean value or something like that at each data point of a certain input feature. But sometimes it's not sufficiently representative, and what we are doing in these cases is to consider probabilistic forecasts as input. So we are considering the multiple quantiles of this prediction, and it's working quite well, and it's especially, I think, important to do these things in models that are used in MPCs, because there the uncertainty on this type of models makes you our capital for making a good or a bad MPC.
Okay. What about you, Fernando? What's your opinion about this question?
Well, we don't have that much experience in using this kind of inputs coming from models, from predictions of models. But of course, when you use machine learning, you always are based on the data, and the data, you have some error always in your data. It may come from the fact that this data are generated from a model or from predictions from a model, or as in our case, these errors may come from the measurement error of the device itself, and that's something that you will always have. I mean, to some degree, and this is something very important to keep in mind, because sometimes we try to optimize, improve refine our model, trying to be more accurate. And well, you need to keep in mind that we cannot more accurate than the data we have. So sometimes we try to refine, and we have a problem in terms of the quality of our input data. And so that's like a limit of our model. And that's something that, of course, needs to be taken into consideration. And that's something that we will always have. Of course, I guess that in these two projects, I guess that the input data is taken under controlled environments, and probably have not so much uncertainty or not so much error. But still, I saw in these some curves that you show that there's some noise. So the experimental data do not follow perfectly this curve. So I guess that you may also have something like that. So yes, the quality and the accuracy of your inputs needs to be considered. And it's not an easy topic to deal with. And again, it's important to know about the process, about the device, about the what's going on.
Yeah, I completely agree with you. I think that we are running a little bit out of time, so let me just move towards the section of questions dedicated to numerical modeling. In particular, we will be focusing on finite element methodology. And this first question is related with something that I've been introducing at the very beginning, or that we've been introducing at the very beginning of the technical part of the webinar, which is the coexistence of the experimental information and the use of these experiments data into the finite element models. So the question is, do you think that if there is a good integration between the needs of the finite element models and the experimental technology? And now it's time for Carlos and Alvaro to give their opinion about this question. So I don't know, maybe Carlos, for example.
Yes. Well, there is obviously needed of integration of between both experimental data and the models, because at the end, as we said at the beginning of the seminar for machine learning, in order to provide a good model or to use a good numerical method, you need to use good data, good quality. So both, they need to be integrated in a common sense. I mean, doesn't make sense if, as a quick example, if you are measuring pH, get a negative value, because you know that makes sense. So at the end, the use of finite element methods, such, I don't know, instant Rapson, in example, gives a really good tool to test the data and validate them. Obviously, you need finally the experimental data to contrast and be sure that your model is working well, as your methods are describing well the system.
Yep, I completely agree with you. And what about you, Alvaro?
More or less the same. The only thing to remark from my experience is that usually the experimental information that we have is not enough to calibrate all the parameters that a compressive numerical model requires. So usually we need to use additional information from literature or from previous experiments, previous research, better say. And a good example, for instance, is the work that you showed in the model for the fatigue model, because you have these standards to obtain macroscopic parameters of properties, and once you move to this more compressive model about composite, you need this rule of mixture in order to predict the material of this composite, the properties of this material, composite material. So at the end, the usual experiment are not enough to provide all the information that we need for really detailed or compressive numerical models. That is my experience, that's my opinion.
Yeah, I completely agree with you. And in fact, I once when I wrote that question, I was thinking really in this aspect, mainly because as you've seen, we only ask for 3 types of tests: force displacement, which is a standard one; end results, also a standard one. But then this is not enough really to characterize the behavior of the material. So the key question, I mean, yeah, the key question here is really the standards prepared for the necessity of the numerical framework? And I would say not really, because and this is just when you are talking about metals, but then when trying to move to composites, then this goes even worse, because things are not really prepared for the demands of the numerical technology. So yes, this I completely agree with you. And of course, it's like we need to advance into this direction uh, to introduce this necessity into the standards to better characterize the models that then will be used to simulate and all these processes that we are studying in the projects. So yeah, I completely agree with you. Then the next question is related with the optimization task, or the optimization possibilities that allows the FEM technology. And it says, what role can finite element method tools play in optimization tasks? And I would like to know which is your opinion. So, for example, let's start with Carlos.
Yeah. Well, this is one of the best solutions right now to improve optimization processes, because at the end, these methods are iterative. They go through the data, they try different equations or models, and finally they give you the best result based on the previous one. So at the end, this is a optimization task. So by enabling engineers to evaluate these design and numerical solutions, you can provide a good knowledge and optimize your system looking for using the numerical methods.
Yeah, I completely agree with you. And it's not only optimizing, I mean, it's not that we can only optimize geometries, for example. So
No.
Thinking in topological optimization, but we can also, and I guess that this is the key point of the numerical technology, that we are working on the optimization of the process itself. So we are allowing to reduce times, to reduce costs, and this is really, really important. What about you, Alvaro? What's your opinion on this question?
I just only add that we also reduce experimental work, as you mentioned before. So because once you have a good calibrated and validated model, we can perform the optimization, we obtain in principle, better solution or even the best solution. And maybe just with one experiment to really check that the solution is best than the others or better than the others will be enough. And when we have this model or this optimization tools, we can also perform parametric studies. So just to look for the most critical variables. So in principle, I agree with the fact that they are really useful in order to improve or to enhance not only the technology, but also the general process, properties, and so on.
Okay. I completely agree with you. And then, based on this question, in fact, the next question is, okay, but then which are the minimum requirements to define this desirable finite element method tool that allows us to work in this direction in all these fields? Again, Carlos, please.
Yeah, well, as you know, the problem of this mainly is the computational power that you have, because and the computational power and the data because we are always talking about data, but it's true that this is the most important part, more than maybe the method that you are applying, because method can be improved based on results. You need to get a good data to improve it, and to perform this kind of experiments, you need not big machines, because at the end they are working with CPU rather than GPU, but you need to have a good power machines to try to model of this and to get all the variables into the model. So that's what I get, I guess.
Okay. What about you, Alvaro?
More or less the same. That is mainly the main problem of these kind of tools. They require computational power in order to obtain the solution. So it is complex to have this equipment outside the research field. So it is complex. For instance, maybe we can use just this detailed tooling research in order to have a really view of the process. And then in order we could try to develop some simplified version for industrial uses or these kind of things, just because they require a lot of computational power in order to obtain a solution in a reasonable time.
Yeah, I completely agree with you with this last part. And in fact, something that it's I find kind of surprising from my point of view is the fact that yeah, we are providing all this really advanced technology, and we are developing all these advanced methodologies to really study all these topics. But then when moving to industry, for example, not of course not in all cases, but mainly or in particular in the case of the Fatigue4Light, what we find out is that everybody is studying such a complex phenomena like the fatigue using linear elastic models. And this is kind of weird for us because it's like, okay, we know that we have a quite powerful tool, that we are developing a tool that allows us to go really into the study of non-linearities in terms of damage, plasticity, finite finite strains and displacements, and also, of course, taking into account in a continuous way the study of fatigue and so. But then, when asking for the industry, they are just interested in obtaining one number, and this can be obtained with just a linear elastic simulation and a regression tool software, and that's it. So it's kind of weird, or I mean, we need also to understand what you said previously, that this really advanced technology cannot really be used always, mainly not only because of the high dependency of having these high resources to undergo the simulation and so, but also because sometimes everything or some part of the study can be directly solved with just a simple tool. So yeah, this is something that we've been thinking quite a lot in our group when starting the project. Okay.
Sergio, can I make a comment
Yes.
about the second
Yeah,
question?
sure.
No, because you're going too fast. I missed it. It's just a comment. It is obvious that if we are in our own, let's say, garden of finite elements, it's easy to optimize things. No, I mean, we can try with several setups, even with topology optimization, as we mentioned. But in the Fatigue4Light, we won't have time for this. Maybe in a new project, who knows? But it is actually a problem that, for example, I'm thinking in automotive industry. Okay, there is a coexistence of two worlds: our finite element world or modeling, and the design world with CAD. Okay, and it is actually a huge problem because if you start working with them, they're going to send you CADs. Then you are exporting, generating the mesh. Then you can optimize your own things based on your experience. But the workflow is failing in modifying this garden that you have according to the necessities or according to the design models that they have. I know that, I mean, in another project that we have at ThemeNet, we are going to focus on this. It is called isogeometric techniques, no? That were proposed, let's say, 20 years ago, something like that. But I just wanted to make the comment that, okay, we can optimize in our field, but sometimes it's difficult to transfer this to industry because they work with different tools and different mindsets and with splines, you know, and so just wanted to comment on that.
Yeah. Completely agree with you, Alejandro. Then I'm not sure if you want to add something else, Carlos and Alvaro, for this part, and also Fernando and Gerard for the machine learning, or you want to comment something else to the other topic. If not, we can move then to the horizontal questions. Okay. Then these three questions that we prepare for this horizontal questions part are just dedicated to more or less connect and to identify some ideas, common ideas, or share ideas that we can establish between the machine learning and the finite element method. And the first question, I know that we've more or less talked about this in the previous slide, but I would like to summarize the limitations that you have identified in the current machine learning and finite element method tools particularly in this optimization operations. So I don't know, maybe Gerard, you can start answering this question now.
Well, first of all, I'm not an expert on this part optimization, but it's okay. But with the presentation of David and Lucia, I think that one of the limitations of that approach is what I was talking a few at the end of his presentation, that how you can assess this quality of the piece or the part that he was providing only a okay status or not okay status. So I think that if we manage somehow on defining quality in other terms, in continuous terms maybe, then I think that would be greater the results on this approach, because MPC, so model predictive control, it works really well when you have a model, an industrial model in this case, that it's like confined. There is no user behavior disturbances and and all these things. And I think that this approach could work really well if you can manage to define a more complex output for the machine learning model.
Okay, thank you. I wonder if Fernando wants to add something to
Yes,
this.
I think one of the limitations, and it's related to what was mentioned before, is that these new techniques and methodologies, tools, it's quite often it's difficult to move them into production or to make the industry use them. I mean, you mentioned that before, and on one side, it was good for me to hear that, because we found the same situation, although the situation is sad in a way, in that you make a great effort in trying to improve something, some process, some methodology to demonstrate that it's better than what is in use. But after that effort, quite often the end users, let's say the industry, prefer to keep with their own all the procedures which they have been using for some time. They may know their limitations, but still, there's a need for it's very difficult to make them go
Switch
further.
from one.
Yeah. So I think this is a limitation, both for the machine learning part and also from what you mentioned before. If we think about this advanced or complex numerical models, I mean, it's clearly this simple models are clearly wrong. I mean, and there are tools there that you can use, and it has been verified that they are better. But still, I mean, maybe we need to communicate better. Sometimes these methods are too complex for the industry to understand, so they don't understand them well, and they prefer to keep their own procedures. I think this is an improvement. Of course, this is going to improve in the future. This takes time, and once people making decisions in the industry are more familiar with these tools, it will be more, easier for them to adopt them and use them. But at this moment, I would say this is a difficulty.
I really hope so. I really hope so. Then what about you, Carlos, please?
Well, this is what we said before at the beginning. We are living in the era of data, but many people doesn't share the data, and we have many problems to integrate numerical models into machine learning pipelines. Why? Because as we said before, the format, the information that they contain, is not always the correct one. Let's say, I mean, example, designing several parts for vehicles needs different treatment, depends on what you are gonna do with that part. That's why sometimes you want to optimize, but you don't have the real input or all the information. So we have many limitations right now, but it's true that many people is working on that. We are using a lot of open source programs. That way we can share and translate the information into useful for us or for them models, let's say.
Yeah, I completely agree. And what about you, Alvaro? What's your opinion about this topic?
I think that in general all the aspect has been covered. So maybe just focusing on a specific problem on finite element models is that maybe even if you develop your complete mathematical model with a complex equation to represent the physical phenomena, you try to validate it with experimental data that can be good or bad or something in between. And maybe at the end, after all this effort, your model is not good enough to obtain a good representation of the process or the property or whatever. So at the end, it's not really useful for optimization, and then you have to move to something in between empirical or machine learning model and the finite element model. So one problem of finite element models is that sometimes you think that you know well how the process is or all the things that happens are known, but at the end something is missing and the performance is not good.
Yeah, I completely agree with you. Okay, I think that we can move to the next question, which is, I think that more or less we started to address it, which is about the coexistence of the two tools. The question is, what should be the framework for machine learning and finite element method models to coexist? And the idea for this question is to know if you think that there is a scope, an opportunity for using both of them together to combine both, or do you think that at the end only machine learning will be used or only finite element method models will be used? I would like to know which is your opinion. So we can start now by Carlos, for example.
Okay. Yeah. Well, the ideally framework should be work with them right now, because one is let's say moving the information, the other one is analyzing and interpreting, but both can exist together. The problem is what you said, in which framework or which is the scope of this framework, because at the end in this case in Fatigue4Light, in example, we have a lot of experimental data. You have a good numerical methods to analyze that data. In that case, both methods can coexist because both fulfill the requirements for each other. But it's true that this really depends on the scope of the main idea, because sometimes you only need machine learning methods to go for a solution, and the opposite. Sometimes you don't understand nothing at all about machine learning, and you need to use finite element analysis or methods to try to figure out the solution or find a pattern, or let's say whatever about your model or your processes. So to coexist, it's true that they can be, but you need to be sure your idea or the scope of your research, let's say.
Yeah. What about you, Alvaro? What's your opinion about this?
More or less the same. It depends on the situation or the case that we study. So, for instance, for process model, I think that in general the numerical model are always a good option, because we want to study a complete process. We are not just interested, for instance, in the quality of the final product. We are also interested in energy consumption, material consumption, and so on. So we will need mass balance and energy balance, and in principle, a good numerical model includes both of them. And sometimes the machine learning just focus on trying to optimize something using some input variable, but they don't have to cover all the energy or material requirements. And vice versa, maybe you want to develop a machine learning model and you need some physical constraints, so maybe the numerical model can provide these physical constraints. Or as I mentioned before, maybe the numerical model is not good enough and you need to complement it with some numerical empirical or machine learning approach to improve the performance or the simulation of this numerical model. So in principle, I think that both can be together, but of course, it depends on the case or and the end of the study.
Okay. Okay. What about you, Fernando?
Yes, more or less the same. I think that both machine learning and finite element models are tools which we can use, and depending on the problem we have, it's better to use one of them or the other, or to combine them one way or another. Of course, I would say there is a trend in general. I'd say there is a trend towards machine learning in the sense that we are having more and more sensors and data, and some fields in particular, more data from our phones and so on. So for complex problems, maybe there's a trend towards data-based models, but there are still problems, more control when we know more about the physics, and in which, of course, finite element models are better. But even in these cases, machine learning may help in us when we're talking about high computational costs or very, very complex calculations, which maybe they can be combined. But well, there are tools which we can use depending on the problem, more or less.
Yeah, I completely agree. Just if you wanna do any other comment, Gerard.
Yeah, well, it's it's all set, and I agree. I agree with all of them, but only add maybe that well, in our field we also used deterministic models and machine learning models in both of them. So I think that always the combination it's a good thing because one provides what the other lacks. And regarding the machine learning models, maybe we have to put the focus a bit on the on multiple input and multiple output models that are also really important. I think that in this field that are you talking about, and because then you can deal with multiple objectives, no? So imagine the consumption, the energy consumption, or some temperature, or some pressure, some of the variables could be modeled at once, or somehow coupled. The model itself can be coupled in some manner, and be used at the same time. No, so well, I think that it's all set with this answer and the answers of the other people.
Okay. Yeah. And the final question is really related with this previous one, and with something that Fernando has already mentioned, which is the current trend in the research projects in relation to numerical methods and machine learning. And we would like to know which is your experience on this regard, which is this tendency, if you identified any, in these research projects, maybe at the European level, but also at national level. So, Fernando, as you have already introduced, or you mentioned already this, if you can give us more details about this.
Well, I wouldn't dare to say what's the actual trend. I mean, from my experience, and this is a webinar, I think, and these two projects are good examples of how both technologies are combined and are used for solving a given problem. I would say that there's a clear trend towards using more data-based models. I remember when we started working on machine learning, like 10 years ago, inside ThymNet, very few people even knew about what big data or machine learning was. And now, because well, you probably know that in ThymNet, we're experts in developing numerical models, finite element method and other approaches. So As I was saying, many people didn't know about machine learning, and now there are more and more people not only knowing about that, but using machine learning in combination with finite element methods and other numerical approaches. And if you take a look at, for example, the biggest conferences on numerical methods, you can see a number of sessions devoted to machine learning, to combination of machine learning, and this is something that didn't happen not so long ago. So there's, in my opinion, a clear trend towards combining both approaches. What's going to be the future trends? Well, no one knows. We know ChatGPT now, endless possibilities. Who knows? I would say that our role as engineers or as is to get to know the best way of using these tools. I mean, of course, there's going to be a need for very focused experts on developing these very complex tools, machine learning, but the important thing I would say trends towards people who know how to best make best use of these tools that we're going to have at hand. But no one knows what's going to happen in a very short time, because we are, I think, living our revolution in terms of the capabilities of both of tools in particular, maybe now more of artificial intelligence.
Yeah, I completely agree with you. Yeah. What about you, Gerard? Which is your experience about this?
Well, I think that in the last years, and especially the last 2 years, in my field, there was an increase on the expectation of how we could scale up all the things that we were modeling, either in any kind of methodology at the building level to districts and cities and so on, because there are these the energy transition that we need to do until 2050 and so on, and this process needs to be done with some kind of modeling first, no, in order to define things and to understand how things work and how to electrify systems and how to integrate EVs, for instance. So I think that we have a good perspective from this point of view. But what I really want to put the focus on is that I think we should work on the scale up of all these methodologies.
Okay. What about you, Alvaro? What's your opinion about this?
In the same trend, so it's a clear increase in the interest of developing digital twin of the process based on numerical models or machine learning, just to evaluate this transition, also integration with renewable energies and so on. And was also for process control, this advanced process control in order to reduce losses or increase the efficiency of the processes. So in principle, yes, there's a positive trends in this development of numerical methods and also a lot in machine learning or even deep learning.
Okay, and just finally, what's your opinion, Carlos, about this?
Well, I'm agree with the previous answers and also with Fernando, because years ago there was nothing about big data, and we were preparing models from the draft, from the scratch. That it was really terrible. And right now there are a lot of tools, a lot of computational, let's say, guidelines to solve any problem that you can face. So, and right now with ChatGPT also you can check how technology have been or have increased with the machine learning and numerical methods. It's true that in example from my side in computational chemistry and let's say material designing, it get a big impact all this because we have a lot of experimental data that we couldn't previously analyze due to the vast amount. Right now, thanks to the algorithms, thanks to the methods, we can analyze and perform and check or find patterns that we couldn't see before. That's really good. So it's increasing these both fields, and we don't know where we go. But it's true that we need maybe to improve our math level, because it's true that many people try to solve the problem without having the knowledge to do it. So that's the only point to do with this.
Yep, yep. And as you mentioned, these two projects are a good example. And I guess that we will not be stopping, or the Europe at least won't be stopping of proposing this type of projects in which both machine learning and finite element method technology will be required, both individually but also in a combined way. Okay. With that last question, we finished the questions that we've prepared to initiate this panel discussion. But now I think that we have still 10 more minutes or so to answer any question coming from the audience. So I would I cannot see now the chat, but I will stop sharing my screen and moving back to the conversation. And in fact, we've been nearly 1 hour talking or with this panel discussion, so maybe it's enough for you. And we've covered more or less everything. And so I guess that we can proceed with finishing this webinar, Andrea.
Yeah, I think you resolved all the doubts. Thank you all. Okay, so we have reached the end of our webinar after an stimulating discussion on how machine learning and numerical modeling can contribute to the new materials development for electric vehicles, leaving us plenty of ideas, information, and visions to reflect upon. I wish to thank our speakers whose presence has been precious in making this webinar a success. And for sure, on behalf of the Fatigue4Light and the Revolution projects, I would like to thank you all for joining us today. I hope that what we share with you was interesting and helpful for you. Okay, so that will be all. I would like to wish you a nice day and take care. Thank you all for joining. Bye.
Thank you. Bye bye.
Bye bye.
Thank you. Bye bye.
Bye bye.